I'd like to thank everyone for joining the webinar today. My name is Ben Sawyer, and I will be moderating today's event. So we're going to go ahead and get started. So today's webinar is choosing the right machine learning methods. And today we're going to talk about what you need to know in order to choose the right machine learning method or methods for your given situation, and how to define what the right method is. Our objectives for today are twofold. First, we want you to take away a better understanding of how to approach the selection of machine learning methods. And second, perhaps more importantly, we want you to leave with ideas, concepts, and questions that you may not have encountered before. So our presenter for today is Dr. Alexander Gray, CTO of Skytree and professor for machine learning at Georgia Tech. Alexander is also a member of the highly respected National Academy of Sciences Committee on the Analysis of Massive Data, and has worked in the machine learning group of NASA's Jet Propulsion Laboratory. He has won or been nominated for a number of Best Paper Awards in Statistics, and is a recipient of the National Science Foundation Career Award in 2009. And now I'd like to turn it over to Alex.
Okay, great. So thanks everyone for joining. Okay, so first, who are we? Well, Skytree is a relatively new company. We've been around for about 3 years. We came out of stealth mode earlier this year. What is our purpose? Machine learning for the enterprise. And I put finally here because since I started in data analysis about 20 years ago, nothing has really changed in terms of the fundamental paradigm for the software and software architecture, making everything essentially non-scalable that you can obtain now. And there's really no commercial or open source project that we're aware of that meets the needs of real high-performance machine learning, meaning high performance both computationally and statistically. And our goal is to empower the data scientists with bigger guns, basically. So you can see our technical advisory board here. We're serious. These are all world experts in their respective areas. And the goal of Skytree is to bring the true state-of-the-art research world into products. So just briefly, what is our product? It's what we consider the first general-purpose massive data scalable machine learning server. Does the heavy lifting of the machine learning. It's not the front end, it's not the back end. It works basically with any common back end database through flat files and so on, and we call it the Linux commands. It's very simple to integrate into anything. So where are we basically, roughly the history, just briefly, of machine learning? Well, in some sense, it's finally arrived. It's, in terms of wide-scale adoption industry. The 50s and 60s and 70s, a lot of the work occurred under the goal of AI. So a lot of it was research, really research-driven. A few, applied. It started to happen. We have may or may not know all your mail is delivered by machine learning. A number of things started to appear in the 80s and 90s with the advent of neural networks, which really was synonymous with machine learning for at least a decade and a half. You started to see other big successes like speech recognition and so on. And in the sciences, more use in the sciences. And today, really, it's kind of everywhere in every industry. And you see really major high-impact systems, like Google uses it to select what ads show you. Netflix uses it to decide what movies to recommend to you. So. Okay, and by the way, when I say machine learning, I mean I include multivariate statistics, data mining, pattern recognition, advanced analytics, predictive analytics. It's really all the same thing. It's the same underlying theory and basic methods today. So there does mean there are different cultures of people who emphasize different things in their research and work, but really it's all the same body of methods. So you all know what your applications are, but in case you don't know, it is being used everywhere already today. Often it's just by the very leading companies in their space. So really, just the tip of the iceberg. We expect a 1,000-fold increase in the use of machine learning everywhere by all companies in all areas. Okay, so we'll jump right to it. So how do you do machine learning? Well, 7 steps to great results. I first put 7 easy steps, but they're not necessarily that easy. So, and some of these may seem obvious, but it is useful to pause on them. Number 1 is to understand your goals, and that's why? Because there are many different choices you can make in machine learning. And if you haven't paused to really think about your goals, then get confusing. So we will touch upon that in this talk. Number 2 is easily the most time-consuming of all of the steps. It takes at least 80% of the time, in my experience, no matter what your expertise level. Just obtaining the data and preparing it. And in here, also embedded is the selection of features, which is a whole black art in itself, which we won't talk about in this seminar. We have some questions. We answer questions ahead of the seminar, and many of them are actually about this, the feature engineering aspect, which is highly important. Arguably, it is the single most determining factor in your accuracy. It's whether you pick good features. But that's beyond the scope of this talk. We are starting from the standpoint of you've already chosen your features. How do you get the best out of them? Okay, understand your data. This is something usually completely skipped in the culture of machine learning. By this I mean what's normally called in statistics exploratory data analysis. That means before you start predicting something, even if you know what you're trying to predict, you look visually at your data with a number of tools, essentially unsupervised learning tools and other kinds of visualizations. Again, the potential subject of a whole other webinar, but which we're not going to cover here. Then you choose your machine learning tasks. I'll give you a finite number of them, even though there really are many, many of them, many possibilities. And then, given your task, you choose from among the available machine learning methods, and I'll give you finite lists for those, even though there are actually thousands. And then you run it. But that's not so simple. Whatever you do, you have to run it thoroughly, or else you don't really know what's going on. By thoroughly, I mean at the minimum, you've tried all the possible parameter settings in order to find, within your amount of time you have available, that can hopefully maximize, squeeze the most performance out of your machine learning method that you picked. If you just tried a few and you've just tried a few for a different method, you really can't conclude that one method, say, is better than another. Okay, and then obviously then understand the results, and there are various ways to do that, various scores and metrics and so on. Again, the subject of a whole other webinar. We won't be covering that. And then then you've learned something and you're probably not done. You probably need to go back to one or more of the steps and repeat. You may need to go all the way back to number 1 and reframe your goals once you've learned some stuff. You may need to go back and prepare more data. You may try to understand more about the data and so on. Okay, try different tasks and try different methods. So in this seminar, we're going to talk mainly about number 5, how to choose the machine learning method. But to get there, we have to spend a little time on number 1 and number 4. So why do we need something like this webinar? Well, it's kind of a shame, but essentially the existing sources and are incomplete. We can't really find this information. And even, of course, I won't be able to tell the whole story just in this short amount of time. The other thing is the sheer complexity of this question. It really, first of all, does get into deep theoretical questions, which I'll just touch on. But just even from a practical standpoint of choosing among the existing options, there are thousands of machine learning methods. Every year, hundreds of new machine learning methods are proposed in various research conferences and journals. And so the state of the art is always quickly moving. Unfortunately, what's in current software is either extremely old or not, otherwise not state of the art. There really is no package that I would call even close to the state of the art. We're trying to fix that, of course. So the existing sources, well, why can't you just crack open a textbook? Well, textbooks are written for researchers generally, not practitioners. And researchers are, by and large, not practitioners. Mostly just come up with new methods, new theorems and stuff, which is what they're supposed to do. More and more there is a culture of trying to show results on real data sets, but no researcher ever has to really solve a practical data analysis problem, generally speaking. And so they don't get all the way into the guts of it, in my opinion. There are some attempts at practical guides. Unfortunately, in my opinion, they're inexpert or incomplete. They don't have the expertise of, say, researchers. So they're really just these two worlds that neither one is sufficient to answer this question. The other thing is, as I'll try to get at later, there are hidden subjective biases. People live in certain philosophical camps, and me personally, I'm a pragmatist. I will use kind of objective criteria, that's how I think, that are pragmatic, we'll talk about, as opposed to subjective criteria. And I'll give you a feel for what some of those are. But anyway, many authors who really try to give advice, it's because they're trying to push a certain conceptual or philosophical camp, unfortunately. What about comparisons? There have been a few comparisons that try to answer this question empirically. Unfortunately, you can try your own, of course. Fair comparisons are difficult, even if you're trying to be fair. And one is that you may have limited knowledge of the actual state of the art of certain methods. If you compare things like speed, well, the actual implementation really matters, can make orders of magnitude of difference. So everything has to be done in the same trusted software base in some way. That doesn't exist. Not one that one could trust represents the state of the art. And thorough comparisons are large efforts in general. So really doing things thoroughly means trying thousands of parameter settings. And really even going into the feature space potentially. Okay, competitions, which are kind of a little fad happening now. Well, it can neither be called thorough nor fair because they all use different software, and they're not meant to be comparisons. They're you just tune your own thing as well as you can. There's no guarantee that somebody else who represents a different kind of method has tuned their thing as well as you've tuned yours. Okay, so that's a summary of why. If you're confused about what the best method is, not your fault. These are some of the reasons why the answers are not easily found. So first you have to pick your machine learning task, and I apologize if anyone is actually more of an expert level machine learning practitioner. I can touch upon expert level questions if you want in the questions period, but if you really have a sort of expert discussion you want to have with us, we'd love that too. But that's probably out of the scope of this seminar. At least what I'll discuss in the slides, so we can talk to you offline. Just contact us. Okay, so what are your common tasks? I get 7 here. There, of course, depending how you want to list them, there could be hundreds. For more specialized types of goals. But the very first type of thing you want to do that goes beyond simple plots and queries is multivariate queries. So by that, I mean things like finding similar objects. I have an object of interest. They find the k closest ones. That's a multivariate query, meaning it's not something you can do in SQL very easily. Density estimation, that arguably is your first and most fundamental statistical task. That's essentially, I have drawn here a little cartoon of your data matrix, where the rows are your objects and columns are your features. And the colored one at the end, that's your special column. That's what you want to predict if it's a prediction problem. Now, almost all of these can actually be cast formally as prediction problems. So, in fact, even unsupervised things. Okay, so you can formally say machine learning is prediction, no matter whether it's supervised or unsupervised. Okay, so density estimation, for example, you can say it's prediction of that special column where that represents the likelihood or frequency of each object. Some kind of number that just says how relatively common or uncommon that object is. Okay, that's the density. If you're trying to predict if that column is a discrete variable, a category, you're trying to predict it from the other column, that's classification. If it's a number, continuous number, you're trying to predict it from the other columns, that's regression. If you're trying to squeeze the number of columns, maybe it's too high. Really, for example, 2 or 3 is all you can really visualize. Say you want to reduce it to 2 or 3, but somehow keep the same relationships between the points or rows. Call that dimension reduction. Most people know clustering, finding natural groups. There you can consider that special variable, the colored one, as the cluster label. So find some labels to stick onto each row such that you make natural groups. The 7th one we won't really talk about, but I included here in your what I consider the more full arsenal of machine learning methods. When you get to more serious data analyses, you often want to compare data sets. You want to do things like ask if 2 data sets came from the same distribution. And sometimes you want to fuse data sets, which involves some kind of matching between rows, which I also include in this category. Okay, but it's a little less common, so we're not going to talk about it too much. So again, it's actually a lot of knowledge can go into choosing your machine learning task. So even the last slide really is worth a whole webinar in itself, because there are many ways that you can CAD. It turns out there are ways to turn regression problems into classification problems, classification into regression, into density estimation, and so on. There are ways to formulate the same problem in terms of multiple tasks. Okay, but let's assume that you've chosen your task. Then you have a set of possible machine learning methods for each task. Here, I've got a sort of a best of list, my own best of list. This is a of course, debatable. There are really many methods, including many that we have published as research methods. But these I've selected sort of based on popularity, and a mix of popularity and sort of my, in a few cases, my sort of general feeling that about it, its efficacy. Okay, so there are a few here that aren't really very common, but I throw them in because I think they're very useful. Okay, so the first one, we won't actually, the most common version of multivariate querying is nearest neighbors. We won't talk about that because it's not really a statistical method per se, not really a prediction method. It's more, at least in this context, just a query. We will talk about nearest neighbor classification when we talk about classifiers. So density estimation, your most common method is probably a mixture of Gaussians that's used most widely in practice. I throw in this funny one. That's a new one, a recent one, published last year, called density estimation tree. That is basically the natural analog of a classification tree or a regression tree, except for density estimation. So that's why I think it should be added kind of to the standard canon of machine learning methods. It's just a natural extension of other methods for other problems. And it has similar advantages and disadvantages to those methods in their respective problems. Kernel density estimation. For classification, that's probably the most widely used and useful overall machine learning method or task. And so I'm going to go into 8 different options there. In gray, I've listed just a few things that I would also add, kind of present more of a complete picture, but we won't have time to get into them. They're generally a little more obscure slash specialized. And so on. In regression, you see a theme here. One theme here is that I've kind of listed them roughly in order of simple to more complex, but if only very roughly. It always starts with linear methods, and then we go into nonlinear methods. And I'll say a little bit more about that. And again, if you don't see your favorite method here or one you've been curious about, you can ask about it later in the Q&A, and if you want to say why I didn't include it in the top in this list. It doesn't mean it's not a good method. It just probably means it's not popular or of general applicability. And clustering, and like I said, we won't talk about testing and matching. Okay, so this in blue, these are the methods that we'll go into one by one, and we'll look at where they fit in the trade-off space that I'll talk about. So these are the main 4 axes that I use to think about when I'm looking at a new data analysis problem. And by now, over the last 2 decades, I've probably looked at 100, 150 different data analysis problems. So number one, generally speaking, for anybody, is always accuracy. In other words, how good is the prediction? Your method says, and like I said, all of the, and say that generally because all of the machine learning tasks can be thought of as prediction tasks, even unsupervised tasks. Okay, so there's a notion of accuracy possible for every one of the tasks. Okay, of course, if second one, speed. This is these 2 are probably the most important, generally speaking, for most people. Number 2 has become to the fore recently because people have realized they have a lot of data and that they want to use a lot, as much of their data as they can, and that current tools often fall short. So it's a big concern. This is one of the big motivations for our company. We provide fast algorithms for things, and as well as state-of-the-art statistical methods. So now, accuracy I always leave as number one, because there's always a way to go faster by computing approximations, and if you're not extremely careful, you're producing garbage, and there's really no point producing garbage. You get low accuracy. So speed always has to maintain accuracy as much as possible. So generally speaking, there's a trade-off between accuracy and more about that. Number three is, and by the way, on speed, there are at least two types of performance. There's training time and test time. Training is learning the model. Testing is at prediction time when you're in production. How fast is it to make a prediction for one query point or row that you're asking about, let's say. Okay, scalability is intimately tied to speed. That just means how big a data set can you go to. So memory cost is somewhat intertwined in there too, okay, but we're not going to explicitly talk about that. Three, interpretability. So this is, in many situations, this is kind of the number one goal. So that's trying to understand why a machine learning method made its predictions. Some machine learning methods, you can get that out pretty easily, and some you can't at all. Okay, number four, very important actually, is the simplicity of the method, which means how much fiddling and screwing around that the data scientists need to do. This is sort of all of these things, but particularly this one and number three are a little qualitative, hard to really fully numerically quantify these things. So nonetheless, I will attempt to give you my qualitative categorizations or assessments of different machine learning methods along these axes. Okay, number four really boils down to data scientist time. How much time does it take the data scientist to fully try to maximize the potential of that machine learning method? Okay, now generally speaking, accuracy trades off with each of the other three. Accuracy is usually the whole point, but if you want to go faster, there are many things you can do, but it reduces accuracy generally. Simpler methods are faster, but less accurate as well. Same with interpretability, and the same with simplicity. Okay, if you want to be interpretable, you limit yourself to certain kinds of models that are can be sort of decomposed by a human in terms of their parts, but the most accurate methods convolve all sorts of, functions in opaque ways, unfortunately. Simplicity, again, the most accurate models are highly complex models, and furthermore, if you want to squeeze the most accuracy out of any machine learning method, you tune all of its parameters, tune the heck out of them, which takes time and it's not simple. Okay, there are ways to automate, essentially, and Skytree, in fact, does automate a lot of this stuff, but that, in the end, relates to speed. If you can't run many parameter settings very efficiently, then you won't, and then you won't be able to automate. So I'm going to spend 2 or 3 slides on some other high-level aspects of ways to think about machine learning methods before we dive into the list ahead in blue, looking at the pros and cons of each one. These are, the next 3 slides or so are theoretical concepts, but I'm just going to describe them qualitatively, just so you understand how a researcher thinks about the comparative qualities of different methods. Okay, so this is probably the most important thing. Parametric versus non-parametric. It's a little confusing. It's kind of simple in principle, but it can be very confusing, in part due to the terminology. So parametric, essentially parametric models are simple models, non-parametric models are complex models. But what that means formally, so parametric means there's a finite number of parameters in the model, which is independent of the number of objects or rows. It makes a strong assumption about the underlying functional form. So, for example, any linear method, like linear regression, or a linear classifier, like logistic regression, is a very strong assumption. It says it's linear. The function of interest is linear. Okay. So, for example, in a linear model, there are D parameters, where D is the number of columns. And that's it. It doesn't matter what N is, the number of rows. There are always D parameters. Okay, so these are generally simpler, more interpretable, and they're faster. So there are good reasons to use parametric methods, depending on your goals. But generally speaking, these are less accurate, because it's only going to really have be the best method if it turns out that the underlying function, which you never know in advance, but that true underlying function is that relates your, say, your features to your target class. You don't know what the function is. If it happens to be linear, you would be extremely lucky, and a linear method would be the best possible method for your data. But it's just empirically unlikely. Okay? We'll say a little bit more about how we can make statements about which functions are, whether we can make statements about which functions are more likely to happen than others. The next slide. So, what are among the list of two methods that I showed? All of these are parametric. Mixture of Gaussians, logistic regression, linear support vector machine, linear regression, lasso, principal component analysis, non-negative matrix factorization, k-means. I think I added independent component analysis too. Okay, more or less, parametric methods are what we think of as classical statistics. So it took a lot of work to really understand parametric methods, and much of the theory of statistics is all about that. Okay. However, people like Tukey in statistics started to develop the idea of non-parametric statistics. So it all comes from statistics, make no mistake, but the cultures of people who really like to program computers, kind of, which really started in the double E world in the 70s, 60s, and 70s, 50s, actually, 50s, 60s, 70s, and then later computer scientists trying to do AI, kind of ran with non-parametric methods. It comes from statistics, but it's more computer science people culturally who put a lot more energy into them. Okay, so modern machine learning is mostly about non-parametric statistics. These are models where the size of the model effectively goes with the number of objects. The confusing, and so think of things like nearest neighbor, which is your kind of canonical non-parametric method, probably one of the earliest. The name, or formally we say, they have an infinite number of parameters because we think of the location of each data point as a parameter. But That's confusing because as a user, you don't really set those as parameters. The data are given. What you set is something like K, number of neighbors and nearest neighbor. So nonparametric, confusingly, doesn't mean it doesn't have parameters. There are still parameters. They're not infinite. They're just one in the case of nearest neighbor. Okay, but it means it's not a parametric model. Can affect the upshot is it can effectively fit virtually any underlying function of form. Okay, in the limit as the number of data goes to infinity. So let's say if you can prove that, under mild conditions on the underlying function, which normally has to do with smoothness of the function, then the model approaches the true function. If you can prove that, then it's formally non-parametric. Okay? So the main point is that these are generally more accurate. They can effectively fit anything, but they're more complex, less interpretable, and slower generally. Okay? So if you're wondering what is the most accurate method, it's going to be one of these generally for your, depending on your task. Kernel density estimation, density estimation tree, decision tree, nearest neighbor classifier, kernel discriminant analysis, neural networks, so on, including random forests, boosted trees, so on. So here's another theoretical concept, a couple concepts that really were developed in the 80s. So the first thing you should know this whenever someone asks you, what is the overall best classifier? Say, you say, there's no free lunch. There's something called the no free lunch theorem, which effectively says you can, whatever your for finite data, whatever your classifier is, there's always a way to have data points that screw up your classifier. In other words, there's really no classifier that can do any that strictly trumps every other classifier, always. Okay, that's in some worst case sense, though. Still, that means you cannot say in advance of seeing data, what is, if there's a single best method. Okay, inductive bias was some terminology used to basically say every method has its own different from bias. So I'm not a huge fan of this term, but it means that every method has its own leaning, sort of, in terms of the kinds of functions that it likes to fit well. Think about a decision tree. It tends to fit piecewise constant functions. So functions with sharp discontinuities, perfectly fine for decision tree. For other things, more problematic. It takes more complexity in the model to handle such functions. Okay, so this is basically saying, from a theoretical standpoint, there is no best method that you can say all the time. And in practice, it's also true. There are some conceptual camps you should be aware of, and one of the big ones, and this will be the subject of a whole webinar because it's a complex topic, frequentism versus Bayesianism. It's one of the most common questions I get from scientists when they start to sit down to do data analysis. It's filled with fire from both sides. It's the equivalent of a holy war. But there are objective ways to reason about whether you should be a frequentist or Bayesian. For the most part, everything we're talking about in this webinar is frequentist. Like that, not because I really care. I'm generally agnostic to these types of things, but because pragmatically, if you want to be a full Bayesian, there are reasons to be, aesthetic reasons that argue in the direction of Bayesianism. But unfortunately, it leads to massive computation. You have to compute things in a different way to be a Bayesian. That's generally intractable for large problems and fancy models. Okay, so not to say we don't do Bayesian stuff sometimes, and it's not a good idea, in all cases. But generally speaking, in the era of big data, it becomes much less tenable. There is a new thing that's kind of buzzing around, which is really an old thing, which is a revival of neural networks from the 80s, which I will touch on, called deep learning. And so you may be wondering about that. It's really coming at machine learning from one of several historical standpoints, that being biological as opposed to mathematical or statistical. So the mathematical viewpoint looks at fitting functions and has a whole bunch of theory and so on. The biological standpoint tries to mimic what the brain does or what we think the brain does. So I'll discuss more that in the context of neural networks. But mostly what we're focused on in this webinar are statistical approaches because they are the most practical generally. But they're not always. There are cases where neural nets can be great, which we'll mention. We just want to mention a few other considerations that can completely dominate your choice. That if you have one of these issues, it can decide for you your machine learning method, irrespective of all these other criteria. Sensitivity to outliers. Some machine learning methods are more sensitive to outliers than others. If you happen to have those, that can be a big consideration. The ability to handle missing values. That means in your data table, some of the entries will be question marks. You just don't know what the answer is. Like somebody may not have entered their zip code, just a question mark. Ability to handle non-vector data. That means your data is not structured or a fixed length vector with a fixed number of measurements, but it could be that each object is something funky, like a whole, like a sentence or a string or a tree or a graph. Okay, there are ways to handle that. Some of the methods can handle things like that. Others cannot. The ability to handle class imbalance. This is where in a classification problem, you have one class that you have many, many more data points in than the other. In many cases, in a classifier, you don't just want the answer is class A or class B, but you want the probability of class A and probability of class B. For example, if you're going to estimate the yield of somebody, how much profit is made based on the probability of person buying or not buying. You need the actual probability of buy times, then you can multiply by the price and you can get a yield. Some work better in high dimensions than others. That's a whole complex topic in itself, why that is, how to understand that, and it's not fully understood. Extensions, some can be easily extended from IID data to dependent data. So everything we're talking about in this webinar assumes IID data. When we talk about that data matrix, we're assuming that you can shuffle all the rows and it won't change anything. So if I reorder the rows, nothing changes. That's something you can do with IID data. Dependent data would be something like a time series, where if the rows are ordered, time, let's say it's a stock price, then these methods here don't directly apply, although there is a way to apply them. Okay, so I won't really go into all of this stuff, but you can ask about it in the Q&A. But there's way too much to say about each method there. Okay, so in the next 6 slides, all I'm going to do is go through the pros and cons of each method according to the criteria, we've talked about, and kind of rate them qualitatively. Obviously, this is all a little fuzzy, but this is just my rough summary based on lots of experience. Okay, obviously it depends, but this is an attempt to not just answer the question that it depends, but kind of give you a rough qualitative categorization. Okay, so density estimation we'll start with. So your first most common method that's not too simple. Too simple would be probably like one big Gaussian. That would be a simple density estimate. A mixture of Gaussians. And by the way, you can make this non-parametric. It's parametric, meaning you have to say in advance how many Gaussians. You can kind of make this non-parametric by trying many, many values of the number of Gaussians. That's generally not done in a very principled way, which is why I still use it as parametric. Okay. Accuracy, kind of medium in parentheses here. So very low is VL, low is L, medium M, and so on. I will put in some cases star. That means if you use a state-of-the-art, there's always the vanilla method, and then there's a state-of-the-art version with bells and whistles from the research literature or experience. So the Skytree versions, for example, are state-of-the-art versions. And that's a little different. You can often go up at least one category with the state-of-the-art version. Okay, so there's a way to be more accurate with a mixture of Gaussians. Speed, medium. Train and test, the way to go much faster. Interpretability, that in the context of a density estimate, is simple. It's just a sum of Gaussians, sum of weighted Gaussians. So that's fairly easy to interpret. Simplicity I put to low to medium because a mixture of Gaussians requires an optimization which is not convex, which means the result, how good the model is, dependent on where your starting point was. You give some initial seed parameters. You have no idea whether those are good parameter settings, and then it converges on some answer. And then you keep doing that over and over and over, and you take the best model. That's a lot of tuning and screwing around, and so that's what I mean by low or medium simplicity from the data scientist standpoint. Okay, so in practice, not very automatic. Okay, this funny thing that I've added to the discussion, density estimation tree, that's a recent machine learning method, but in a way it's an old concept. It's the density estimation version of a decision tree. So that takes some wrapping your head around, so we can talk about that later if you want. But for now, suffice it to say that it behaves rather like a regression tree, which we'll see later. Very high speed at test time, like any decision tree, but medium, medium high here. Actually, this should be low. So it is actually slow at training time. Okay? But it's very easy to interpret like any decision tree and fairly automatic. Okay, your most accurate of all this density estimator is completely non-parametric. It's kernel density estimation, high, very high, but in accuracy, slow at training time and test time, unless you know the state-of-the-art way to implement it. Okay? But very easy to interpret. It's just a sum of kernel functions and fairly automatic. It's just one parameter generally. Okay, so here you see all these trade-offs happening that I mentioned. Speed generally trades off with everything else. The classification, there are 8 methods I'll describe, and so I'll break this into 2. So logistic regression, linear method, low accuracy in general. but very fast in training and testing. Okay, very easy to interpret. You just look at the coefficients to see what features are important. Has no actual parameters, so very simple. Thus, be very popular, but people need to know you're not getting the highest accuracy. Decision tree is the first of the nonparametric methods. All the rest are nonparametric. It's maybe the least accurate of the nonparametric methods on its own. I'll put it as medium, but has some very unique advantages. It's sort of medium to high in training speed, very fast at test time. Whether it's interpretable or not, or how interpretable it is, it reads off, the rules read off nicely in a human interpretable way. So I put it as high or very high, but it depends on the size of the tree. The tree has 500 levels in it. It's actually not that interpretable. So, it's pretty automatic. So it's simple. Okay, nearest neighbor starts to get into all the rest of them. I'll put as high or very high in accuracy. Those are all essentially fully non-parametric. Even the simple nearest neighbor can be, especially the state-of-the-art version, which has things like metric learning and so on, can achieve true best accuracy on a data set, as can all of the methods hereafter. Okay, so which one ends up being the absolute best? It really, in the end, kind of depends in practice on how much effort you put into each one as far as tuning parameters. All these have the capability to achieve what's called the Bayes error, or the absolute best possible error for a data set. Okay, generally low, very slow in training time unless you have fast algorithms and a test time. Interpretability high. It's very. We can explain why it's making its decision. It just look at the K nearest neighbors, inspect them, and you can understand why it said this customer is likely to buy. Look at the customers it's close to. Okay, generally only one parameter. Fairly simple and automatic. Kernel discriminant analysis can be seen as a kind of generalization of nearest neighbor, but it has many of the same properties. It's slightly more complicated. It has maybe one or two more parameters. Okay, but it's and slightly less interpretable. So you now have to think about probability functions. Neural networks. I just want to say a little bit about them. Have kind of been revived from the 80s. Again, like all the methods that are non-parametric were shown to be non-parametric in its own funny way in the 80s under the heading of the universal approximation, can be extremely accurate and have some problems still the dominant approach, like optical character recognition. Okay, but it has some big downsides. Generally very slow to train. Testing time is simple, often. Doesn't have to be slow. But the interpretability is a complete opaque black box. A whole mass of sigmoids and other functions that you can't really pull apart. There's a lot of fiddling with the number of hidden layers and all sorts of things. Okay, so it's extremely fiddly, probably the most fiddly or least simple of all of the methods. I've listed next the thing that kind of pushed neural networks out of favor in some ways in the mid-90s, the support vector machine. I list a range here for the different qualitative categories because it depends on the kernel. There's some function you can choose inside it that either makes it a linear model, which makes it parametric, or makes it completely nonlinear and totally not understandable, but highly powerful in terms of accuracy. So it can achieve the very highest accuracy. And it's incredibly hard to beat, actually. For a time, won almost all competitions. Okay, not too complicated, not too many parameters, actually, but generally very, very slow. Random forests, very popular now because they're kind of medium in simplicity. You do lose interpretability over the single decision tree. Now that you have a whole mass of them, hundreds or thousands of them, there's really no way you can say that's interpretable. There are ways to get things out of the ensemble, things like the relative importance of features, but that's not special for random forests. You can do that for some version of that for other methods. Okay, generally it's slow, but it kind of depends. It depends how you set those parameters, number of trees, and so on. Okay, but often you can achieve state-of-the-art accuracy with medium amount of data science work. So that's what's made it really popular. Similar with boosted trees, maybe I'll give it slightly the edge over random forests if you're going to use some kind of tree-based thing in terms of accuracy. Again, depending on how you set parameters, they're really slow or medium and not very interpretable. I'll just kind of buzz through things now. We're getting close to the time. Obviously, linear regression, much a linear classification, low accuracy, but kind of good in other ways. Lasso, just a kind of feature selecting linear regression, more intensive computationally, shares other properties. Regression tree starts their first step, kind of like a decision tree, in nonparametricness, only medium in accuracy. Again, all of these things you can also ensemble-ize, just as you do with random forest and boosting. You can change these properties. Kernel regression is probably your best overall for high accuracy, but slow without fast algorithms. And Gaussian process regression is generally super slow, and even with fast algorithms. And so it is a more powerful model in principle than kernel regression, but generally too slow for data sets, large data sets. I'll quickly go through this on dimension reduction. So all these are linear methods, the first three, and they all share similar properties. Accuracy here is in the sense of reconstruction error. They're fairly fast at test time, prediction time, but may or may not be at training time. The last one is your non-parametric one, high in accuracy, but actually poor in the other aspects because a lot is not understood yet, actually, about manifold learning in terms of being able to automate it and interpret it. And it's very slow, generally. Okay, finally, clustering. K-means is your go-to method generally. It's sort of medium, you could say. It's parametric. It's kind of like mixtures of Gaussians, a lot of fiddling because of the optimization method goes to local options. So you have to keep trying different initial settings. Never really know when you fit the best one. Hierarchical clustering, extremely expensive unless you have fast algorithms in the MQs. But it's actually totally automatic, no parameters, and gives you clustering at all scales. So it's actually quite a good method if you can do it. And then mean shift, last of all, arguably is the most non-parametric. It's basically built on top of the idea of kernel density estimation. So in some sense, it's a very well-founded clustering method, which is always an issue with clustering. Not really sure if it's statistically kind of valid. This has a nice interpretation statistically, so I put high, very high sense of accuracy, but actually not that simple. There's a bunch of tweak parameters and so on, and it's low. Okay, so that's it, actually. I hope we didn't go too fast, but essentially, once you know what the task is, you decide which trade-offs you want to make, understand a little bit about the theoretical kind of characterization of different methods. Then you can go into the pros and cons of each method. I should only one way to really get a feel for it is to try it on your data. How can Skytree help? Well, we make things faster to run experiments. That's actually how you find the best model. You just try them all. But if they take forever to run, that makes it more difficult. And you do want to be sure, or it would help if you knew each machine learning implementation was the absolute state of the art. That's what you get with Skytree. And we do have special ways to go totally off the charts if you want. Ultra accuracy, ultra high speed, interpretability, total automation.
Okay. All right. I'll take it from here, Alex.
Yeah.
Thanks, everybody, for sticking around. I know we misjudged our time a little bit and have gone over. We're going to go ahead and jump into the QA right now. We will answer a few questions even though we're over time. We have a lot of good questions. If you have questions that you haven't submitted, please go ahead and use the Q&A box and submit those right now, and we'll get to those. We'll start answering those momentarily.
Yeah, so one of the questions, in your experience, is there benefit in ensembling various methods? For example, yes. So if you're familiar with some of the theory of ensemble methods, which, for example, bagging is a theory underneath random forests. Bagging says if you combine a whole bunch of slightly perturbed models that are a little different from each other, in a certain sense, it does that through perturbing the rows of the data set by drawing with a replacement from the original data set, and also introduces some randomness in the decision tree going process. Essentially, what it's getting at is reducing the variance in the error. So you can, it turns out you can decompose the error made by, say, a classifier or regressor into at least two parts, bias, so-called bias, and the variance. So that's a whole, can't really, more or less biases means, is your model even capable of getting the right function? And then the variance is how much kind of noise is there around that function that it's fitting. Very roughly speaking, we would have to do a theoretical webinar to really dive into that. But so something like an ensemble method, like a bagging style ensemble method, is getting at the variance part of that composition. And how does it do that? It basically tries to make many models that are very different from each other, different in all the possible ways, kind of dancing around the true function in as many ways as it can. So therefore, and it does that usually with a single type of model, but making different tweaks to it. In other words, like a decision tree, but many different tweaked decision trees, and then it averages them all together. But something like, but it's been shown in limited experiments, not enough work has been done on this, that if you use totally different models, you get even more difference between the models in ways that complement each other. That's what you want. So you can, for example, ensemble a neural net, a support vector machine, and a random forest. And that can help. So that hasn't really been deeply studied theoretically or even empirically, probably because it's way too expensive for people to do extensive experiments with stuff like that. But in some competitions, the Netflix prize, that ended up being the winner. It's some kind of big grab bag of different machine learning methods all combined. Okay, similarly with boosting. Boosting, it's generally done with one type of family of model, like a decision tree, but you can do it with any kind of model, and you can even mix the models. But again, not very well understood, not very well studied empirically or theoretically. But there's some anecdotal evidence to suggest that that can be the best possible method overall. can be extremely expensive. Okay, here's another question. How good are the techniques available to handle non-vector data? So I mentioned non-vector data like proteins, which represent by the whole graph structure of the molecule, and so on, subgraphs of a social network. So say I want to compare two people by comparing the structures of their friend networks. Maybe one person is more isolated and has a certain kind of structure in their social network. Another person is more densely connected or something. And that's how I want to compare these people. Well, essentially the main answer we have today in the machine learning world, there are many other answers, but the main one that people focus on is called kernels. So there are ways to make a similarity metric between graphs, similarity metric between strings, so on, that as long as it meets a certain simple property, we call it a kernel, so-called Mercer kernel. And there's some of these methods in the list that I showed where they're kernelizable. You can pull out the usual notion of similarity between objects and plug in this funny kernel, whatever kernel you want, as long as it's a valid kernel. There's a certain set of things that have been proven to be valid kernels, and there are examples for all of the things I mentioned, strings and graphs and so on. So those include support vector machines, Gaussian process regression, principal component analysis, kernelized principal component analysis, and a few others. You could even do it with nearest neighbor, and so on. So essentially you can get, you have a way to do fully non-parametric machine learning with arbitrary non-vector data. The issue is fast algorithms. So all these things that are kernelized, those are the slowest really of all of the non-parametric methods as of today. So we work on fast algorithms. That's our business, and in the research lab as well. And those, I would say we've made progress, but they're still not what I would call fast. So that's the downside. So if you have, a million, whatever, graphs, proteins or something, it is going to be painful to do a massive support vector machine on them. Okay, but it can be done, and that is a very elegant, you may achieve much more powerful results that way, keeping the data in their natural form rather than trying to squish them into vector form. It is worth pushing that, I think, despite the computational cost. A related question, can you comment on the applicability of the machine learning methods in the list for really large data sets, 100 million plus, for example? Well, so in part that's characterized by, if I put high or very high, then even on one machine, you may be able to go to, if the RAM is big enough, you may be able to go to tens of millions, maybe even 100 million, depending on the dimensionality. These are with the most sophisticated algorithms generally, which is what we have in Skytree. So we have personal experience in that, being able to do ultra-massive data sets like that, even in one machine. But generally and of course, you can always do 100 million if you have an infinite number of machines. Not always. There is some limit, actually, in terms of if your parallelization is not sophisticated enough, eventually communication trumps everything, and you stop getting any speed up from extra machines. But for 100 million, you could definitely do that with a finite number of machines for most of these machine learning methods. But there are the amount of speedup you get from parallelism varies greatly. Something like Hadoop really doesn't get you a lot of scalability, it turns out. Try it yourself. You really, with this size of data set, in practice, swamps that kind of parallelization. But we've done, Skytree, we have a distributed version, and we eat this size of data set for lunch all the time. So, yeah, it's definitely possible.
All right, so let's do one more question. You have and then we'll finish there.
How to make the optimal choice between parametric and nonparametric? Maybe I would interpret that as how do you know in advance whether you should use a parametric or nonparametric? I think that's more. The real answer is you just try different things. Never really know in advance. But if you know that accuracy is your main concern, a non-parametric method, suppose you don't even have Skytree. So suppose you're going to be able to do much less data because of computational reasons with a non-parametric method versus a parametric method. In practice, there's no proof of this, but in my experience, that's still going to give you higher accuracy than parametric method on more data. Okay, so that's a common question I get asked. Well, suppose I don't have a powerful system like yours. Now, do I just stick with my parametric method? I would say still no. I would still go to non-parametric methods if your goal is accuracy. You're only going to be able to do a small number of data, but still likely, my experience, is higher accuracy than a simple method. Okay, so I think that's it for now.
I'd like to just thank everybody for attending and sticking around and asking great questions. And as you can see on the slide, if we weren't able to get to your question, please do send us an email at info@skytree.net, and we can definitely help you out that way. Thanks again, everyone, for attending, and have a great day.